ourselves through it. So first of all, the first step we usually do is isolate the trig function, right? But then we want everything with all sines or all cos, like all the same function. Well, none of that's happening here. So the first thing I was kind of looking at this problem, I was like, does this simplify to be something else? Let's take a look here. So I was like, well, I have cosine of x, that can't be changed right now. We just have cosine of x. Then we have plus sine of x times by tangent of x. What is tangent of x? So we have sine of x divided by cosine of x equals 2. Well then, technically guys, don't we have right now this? Cosine of x plus, we multiply fractions straight across. So then we have plus sine squared x over cosine of x equals 2. How many of you were able to get that far at least? Awesome, that's right, that's good. Then what would be our next step? Yeah, we would want a common denominator. Wouldn't we want to put this into one fraction probably? So let's make this a 1. So then we would times by cosine of x, cosine of x. So now don't we have this? Cosine squared x plus sine squared x all over cosine of x. And that's what equals 2. So then what is cosine squared plus sine squared? So we have 1 over the cosine of x equals 2, everybody. Now I personally just did algebra. I'm like, a lot of people then wrote, well, secant of x equals 2, which is true, aren't those the exact same statement? I don't like having to do secant. I like sine, cosine, tangent. I'm going to change that then. What is this an equivalent statement to? If I want to make this cosine, what can I do? So go back to here, times up by cosine of x, true? And then divide by 2. Does that make sense, everybody? Or if you recognize, well, secant's the reciprocal cosine, right? So we would instead solve, this is going to be easier to think about as when does cosine of x equal 1/2? Very good, very good. All right, well, that's not hard, is it? When does cosine equal 1/2? It didn't give us an interval for which we solve, therefore we're finding infinite solutions. So let's find our x value of 1/2. That happens at pi thirds. And then x is equal to, the next place is 5 pi thirds, right? So we have pi thirds plus and minus 2 pi n. That means at any time we land in that same spot, any coterminal angle, and then same down here, plus or minus 2 pi n. How did the homework go for 7-3 at home? Pretty good. If you have any questions at the end of class today, make sure you ask me. I had someone come get help this morning. I think it was very helpful for them. They're definitely going to know what they're doing when it comes to the exam. So make sure you're coming in the mornings if you need some one-on-one help. Okay. All right, let's do another one. This is number 17 on the homework from yesterday. So just a reminder, guys, if we ever have something inside our parentheses and we're solving, we pretend like there's nothing inside our parentheses. We solve it like normal, and then all we have to do is do algebra to get that x all by itself after we found our solutions. So we're not solving over an interval. We're just solving an infinite solution one. So we're going to pretend like that's just a sine squared of x, not 2x, and just isolate the trig function. So we know that our first step would be to add 1 and then divide by 2. Okay, so we're looking for when does sine squared of 2x equal 1/2. Next step, square root both sides. When you solve and take a square root, you need a plus or minus. So we're looking for when does sine of just 2x now equal plus and minus. And then we know that that's going to be what? Root 2 over 2. Hopefully everyone's okay jumping there because we have square root of 1 over root 2. You rationalize. Now, we literally, guys, just solve it like normal. Anytime there's anything here, solve it like normal and then just take care of what's in front. So we actually have 2x is equal to, the sine is equal to root 2, positive root 2. You split this up. This is two separate problems. It equals positive root 2 where? Pi fourths, right? So pi fourths. And then, where else? Also, you were saying also right here, 3 pi fourths? Yes. Say true. And then, if we're here at pi fourths and 3 pi fourths, we've got to put our plus and minus to pi n. Okay, same here. Now let's go on to the minus ones. So let's look here. We have 2x is also equal to, it's negative root 2 over 2. Doesn't that happen? We always list the solutions on the positive, from 0 to 2 pi positive solution set first. So won't that be 5 pi fourths? And then plus and minus 2 pi n. And then also, so right there is a solution and 7 pi fourths, isn't it? Now, because of how many solutions we have on this one, is it necessary to list all of these? No, if you look where it falls, couldn't we only list this solution and add pi? And that would take care of this one? So I'm going to go ahead and cross out, I think, this one right here, because it's like double dipping, not necessary. This was the 5 pi fourths. This will be taken care of if I, instead of adding 2 pi n, just add pi n. Do you guys see what I'm doing? Kind of fixing.
Pi half.
Oh, you know what? This is a really valid question. I'm really glad you asked that. So you're saying that technically we could just add pi halves?
Yeah.
Fun fact for you, they don't ever do that. They always do just at least pi, which that wouldn't be wrong, so I don't really think I could mark you wrong, because that is true. He's saying if we just list this one and do pi n, that would take care of each little piece. It's just, interestingly enough, I don't really know why, their theory of why they don't do that, they never just add pi. The smallest amount they add, sorry, they never just add pi halves. The smallest amount they ever add is just pi. So, yeah, valid question, but they don't do that.
Okay.
I wouldn't mark you wrong, though. So that's true. Okay, so then also, I'm going to leave this one. This 3 pi fourths would take care of this solution, so I'm going to go back and cross out that one, because I don't need it, and then I'm going to make it plus pi n. All right, now all you have to do is get x alone. So wouldn't we times by a half to both sides to make algebra easier? Oh, maybe, I don't know. This is a good one. I want to know, actually. I swear that the book lists out both. But that is going to be, because now look, aren't we adding pi halves? And, you know what I mean? I'm curious, if somebody wouldn't mind for me going to the back of the book and telling me what this homework solution is, I'm curious how the book would list it. So this is, yeah, I think it's 17. Which, so this is perfect, so we get our pi eighths. Okay, good. Pi eighths, and then we have a plus and minus. Pi halves. N, right? And that's because we distributed. Does everyone see where they're getting that? Did they list the next one as well? Okay, cool. So x is equal to, if we distribute this here and here, that's going to be 3 pi eighths, isn't it? And then plus and minus pi halves n. So yeah, I don't know. I'll have to explore why they don't feel the need of just listing one of them, because technically this would take care of it. So yeah, awesome. Great, great, great. Any questions on that? So don't ever let anything freak you out. Like I saw in the homework, there was sums with pi over 6 right here. Solve it like normal, and then just do algebra to get rid of pi 6. Does that make sense, everybody? So your answers will just, your pi's are going to end up dividing out, but that's okay. Like, we can get solutions as just numbers. Does that kind of make sense? Just go with it. Go with the math, and it's not going to lie to you. So just stick with what you know with math. Okay, awesome. Let's go on to today's lesson. I really like today's lesson. I think it's super straightforward, actually. It really is. So the nice thing is the hard thing is you do have to memorize these formulas for the test. But I actually, once you see the pattern, like I'm going to point out a pattern, kind of. You do have to get these memorized for the test. So these are just more like identity formulas. Technically, they're sum and difference formulas. So once again, it's just a way to rewrite one thing as another. And you can work back and forth. So if you're ever given something of this form, you can write it in this form. And if you're ever given something in this form, you can write it as this form. And you'll see why the benefit of both of these will be once we start doing some examples. So you don't have to write these down because I gave you a trig identity sheet with these already written down for you. I just want to point out a couple things, okay? Even for me, every year I have to rememorize these formulas. That is just part of math, is being good at memorizing. I have to rememorize them myself. So when I was reviewing my lesson to teach this morning, I was like, oh yeah, I do need to remember the pattern. So notice sine of u plus v. I don't like that they use u and v. I mean, we could use x and y. It doesn't matter, you know, but u and v kind of look similar, so I don't love that, but whatever. So front and back, u and v. So notice with sine, it's sine, cosine, cosine, sine. So notice with sine, the sines are on the outside of our formula. Do you guys see? And the cosines are on the inside. And then notice with sine's formula, if it's plus in here, it'll be plus out here. So if it's minus in here, it'll be minus out here. Now notice with cosine's formula, cosine's different. Cosine goes cosine, cosine, sine, sine. Cosine, cosine, sine, sine. And then notice with cosine's formula here, the plus sign is opposite out here. So this will be actually minus sign for cosine. And then if it's minus, it'll be plus. So you just kind of you've got to really write these down, find a pattern that's going to work for you to help you memorize. Now, a lot of teachers don't even give tangent because if we have tangent, can't we rewrite it as sine over cosine? Yeah, you can. To me, I would rather just do tangent, personally. If I'd rather have one more formula and not have to do so much dang algebra with all this stuff. So that's just me personally. But if you forgot tangent, you'd just do sine over cosine, and these formulas would work the same. So look, tangent of u plus v can be written as tan u plus tan v all over 1 minus tan u times tan v. So notice this is a plus sign. With tangent, the sign stays the same on top. So plus, plus, and then on bottom it's going to be opposite. So then it will be 1 minus. And then notice right here, it's a times sign down here. That's a times in between. So just little things to kind of try to get memorized. So the minus sign, if we have it with tangent, if we have a minus sign, we'll have a minus sign on top. The bottom will be opposite of that, and on bottom then they're being timesed, 1 plus. All right, so you have those formulas in front of you for today's lesson, trying to get them memorized. All right, so what we use these for, you guys, is with sum and difference formulas, it allows us to possibly rewrite sine, cosine, or tangent, some sine, cosine, or tangent function that is not on the unit circle with values that are on the unit circle. So that we can, instead of finding an estimated answer because it's not on our unit circle, we can still find an exact answer because we're able to rewrite it with stuff that is on our unit circle. Now, it's not always possible, but if it was possible, we could then calculate exact answers with degree measures that are not actually on the unit circle. Does that make sense, everyone? Kinda. You'll see some examples of what I mean. For example, like 15 degrees. We can only do estimated answers as of now, correct? Because it's not an exact, we don't have exact answers on our unit circle for 15 degrees. But you're going to see now, after we learn these formulas, how we can manipulate our problems so that we can also find exact answers instead of calculator answers. All right, so our goal is to rewrite them in terms of our special angles from the unit circle. So we're trying to rewrite them with 30s, 60s, 45s, and 90s, because that's where these special angles are. So here's my first example. Really, now we're just going to practice. So it says find the exact, keyword exact, value of cosine of 75 degrees. Now in the past, you'd say, well, I can't find cosine of 75 degrees because I can't find an exact answer. I'd have to use my calculator because 75 degrees is right here, which is not on the unit circle. It's on the unit circle, it's just not an exact answer on the unit circle. But we can actually rewrite 75 degrees now as a sum formula or difference formula, depending on what you want to do. So is it true that we could rewrite cosine of 75 with 45, 30, 60, or 90 degrees? Yeah, so let's go ahead and rewrite this. What's the equivalent true statement to cosine of 75 degrees? Okay, so let's rewrite this. This is equivalent to cosine of 45 degrees plus 30 degrees. Those are true. They're the exact same statement. Now the nice thing is, because we have some formulas for cosine and sine, we can now rewrite this in a form that we can then simplify it and find exact answers. So now we're going to rewrite this in this form here. So notice we have, it's always UV, UV. I should go back and just point that out. Notice in your formulas, back to my formulas, it always goes UV, 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 UV. UV, UV. Do you see how it's always front, back, That never changes, so that'll always be straightforward. UV, 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 UV. All right. So we're going to rewrite this. This is the same thing as, let's write it, cosine of 45 times by the cosine of 30. You guys see how I'm just using the formula? Then cosine has opposite signs, so just trying to memorize our formula, minus, and then we have a sine of 45 sine of 30. Now look how that's useful, because we can now calculate exact answers for each of these pieces, can't we? So what is the cosine? Once again, we're trying to keep these memorized, guys. Now we don't have to use our calculator. What is the cosine at 45 degrees? So this calculates to be root 2 over 2. Then we have a times sign. The cosine at 30 degrees is, so we have times by root 3 over 2, agreed? Now we have minus, the sine at 45 degrees we should definitely have memorized, isn't that root 2 over 2? And then times by the sine at 30 degrees, times by 1/2. So that is an exact answer. Isn't this an exact answer? Yes. Now let's just simplify. When multiplying fractions, we multiply straight across, two radicals that are the same, so we can write that as the square root of 6 over 4 minus the square root of 2 over 4. Now I have a common denominator, so let's just put it together as one final answer here. We have the square root of 6 minus the square root of 2. Remember, you cannot call that the square root of 4. That's not how radicals work. You can times radicals, but to add radicals, they have to be like radicals, like terms. Root 6 minus root 2 is not able to be put together. So we have the square root of 6 minus the square root of 2 all over 4. And that is the exact answer. Now let me show you something. Everybody grab your calculator real quick, and I want you to just type in the cosine of 75 degrees, making sure your calculator's in degree mode since you're inputting a degree. And then tell me what the decimal is, just maybe 2 decimal places. The cosine of 75 degrees is? 0.25. 0.26, sure? Okay, cool. Now guys, guess what? This is this answer, but this is like the not rounded answer. If you were to type in your calculator square root of 6 minus square root of 2, hit enter, divide by 4, you will get 0.26. You guys see how this is just an exact answer instead of rounded answer? Cool. Alright, so sum and difference formulas allows us to take something, and if we can, rewrite it in terms of the unit circle so that we can find exact answers instead. Okay, let's do another one. So this one says find the exact, keyword exact. Anytime you see the word exact on a test or anything, that should be like sending signals that say you're not allowed to use a calculator. Unit circle. So find the exact value of sine of pi 12ths. I personally, you guys, do not like to have to think of radians. To me, it's easier to think of degrees and how to rewrite degrees. It's just easier to think about basic addition and subtraction without fractions. So I'm going to convert pi 12ths to degrees. That's 15 degrees, everybody. Do you remember how to convert a radian to a degree? Good. Times by 180 over pi. So that's, we actually are looking at this, the sine of 15 degrees. All right, how can we rewrite that with our 45, 30, 60, 90?
Yeah, 45 minus 60.
Okay, there's many ways. So you're saying, some of you are saying 45 minus 30? Yeah. Okay, true. And then there was 60 minus 45? All correct. So let's just go with 45 and 30, sure. So that is equivalent to, you guys, the sine of 45 degrees minus 30 degrees. True. Now you would say, well, that can be calculated as long as I split it up as an equivalent true statement. So remember, sine goes sine, cosine, cosine, sine. So we'd say sine of 45, cosine of 30. Sines are the same, so we have a minus. And then we have a cosine of 45, sine of 30. And now we're able to find the exact answer. So now we would say the sine of 45 degrees is root 2 over 2, times by the cosine of 30 degrees, which is root 3 over 2, minus the cosine of 45 is root 2 over 2, the sine of 30 is 1/2. So don't we get, once again, the square root of 6 over 4 minus the square root of 2 over 4. So our final answer is the square root of 6 minus the square root of 2 all over 4. Now once again, on a test, you should say, well, did I get this right? You change your calculator back to radian mode or degree mode. It doesn't matter. If you do it this one, you do degree mode, this one radian mode. So you would type in your calculator sine of pi 12ths in radian mode, and then you would go to your calculator and then calculate that and compare the decimals. They should be the same. This one's an exact answer. When you do the calculator, it's a rounded answer.
Is there like certain answers that always go with 45 and 30 because both 45 and 30 are both the ones for 6?
Yeah, true. But yes, exactly. You're going to see that all your answers come out in intervals, with answers with root 6s and 2s, because they're all like, yeah, basically they're going to be variations of this. Does that make sense? Great question. Okay, hopefully that's making sense and how that's useful. Okay, now you guys, this never clicked for me for a long time until it hit me. Well, you guys, not only can we go from this way, it's also sometimes more useful just with all trig identities to work back the other way. Like both sides are good. It just depends on the type of problem. So if you look at this problem right now, we have sine of 42, cosine of 12. Now it says find the exact value. Now the problem is, once again, sine, cosine, cosine, sine. Notice that's a sine formula, isn't it? Now you'd say, but 42 and 12 are not on my unit circle. So the problem is, well, what they're hoping is you'll recognize is, well, this is an equivalent true statement to putting this back together. So let's go the other way. Instead of having it split apart on this side, let's put it back to here. So what's the equivalent true statement to this?
Sine of 42 minus 12.
So let's see if that helps us. Sine of 42 minus 12, isn't it? So then that's sine of 30, which allows us to find an exact answer. So sometimes going the other way is going to help you get to a pretty answer. So sine of 30 degrees is 1/2. The answer would be 1/2. Now, once again, if you were to take your calculator and go degree mode and type in sine of 42, cosine of 12, and then minus cosine of 42, sine of 12, it will come out to be 0.5. So you can switch either way. So a couple more examples. Hopefully this is making sense to everyone. Pretty straightforward stuff as long as you kind of know your formulas. Okay, I need everyone to write this one down in your notes. Now, once again, remember how sometimes I tell you and I would make note to myself, and remember, some of you I think just don't revisit your notes when studying for the test. I'm telling you to make yourself a note that this is one people miss on the exam. So if you write that in your notes, when you see that in your notes and you're studying for a test, you should be going over and making sure you really understand it. And if not, finding some examples in your book, and if not, coming to me and saying, you said this was one people messed up on the test. I don't know what's going on with this problem. Help me out. If you don't. Okay, so let's read this. This says the cosine of arctan of 1 plus arc cosine of x. Now what you're going to have to recognize is this is technically a cosine addition formula, because this is cosine of some u plus some v, isn't it? They're not very pretty u's and not very pretty v's, but it is what we're being asked to do. All right, so now what I would do is kind of simplify from the inside out. So let's rewrite this problem. So we have the cosine of, what does the arctan of 1 calculate to be? I would calculate from the inside out and then split it up. Yeah, so remember, what does arctan of 1 mean? Doesn't that mean what angle has a tangent of 1? And we know that that has a restriction on answers. Tangent inverse has to be answered in quadrant 1 and negative quadrant 1. So we always answer in radians for this. So pi fourths. I guess we don't have to answer in radians. We could put degrees. It doesn't matter, right? Same thing. So does everybody see why this calculates to be pi fourths? Isn't it only pi fourths, everybody? Because of the restrictions for tangent inverse. Okay, now I'm going to say plus. What does arc cosine of x mean? We have an angle that has a cosine of x. That is not a unit circle problem. That's a triangle problem, right? Remember this? So I would say, well, that's really just a right triangle. We put a theta, because that says we have an angle theta with a cosine of x over 1. So cosine is adjacent over hypotenuse. So now I would fill in the rest of the right triangle. So wouldn't we do Pythagorean theorem? So that would be 1 squared minus x squared equals question mark squared. So to solve for the other side, you would square root both sides. So then the simplified answer would be the square root of 1 minus x squared, wouldn't it? All right. So I just simplified the inside a little bit so that when I split apart my addition formula for cosine, it's going to be a little bit easier. So with cosine addition, we can split it apart as this, right? So let's start going. So we have cosine of the front, so cosine of pi fourths. Then we have the cosine of the triangle. So cosine of the right triangle with a theta, an x, a 1, and a square root of 1 minus x squared. You guys see how it's just the formula?
Do you have to go on the cosine?
I would, just because it's not always going to be necessarily cosine, you know what I mean? Well, yes, I just would. Then for the next one we have a plus sign. Oh wait, is cosine plus or minus? It's opposite, isn't it? So minus sine of the front thing. The front thing was pi fourths, so sine of pi fourths. And then it was sine of the triangle. And now all you have to do is simplify each piece. Any questions on how I split that up at least? Same thing that we just did, it's just not as pretty of stuff we're splitting it up with. The cosine at pi fourths is root 2 over 2. So now I'm actually doing the calculations for it. And that's times sine, right? There's a times sign. What is the cosine of this right triangle? X over 1. I've now calculated that. Minus sine. Sine at pi fourths is root 2 over 2. That's a times sign right there. And then what is the sine of that triangle? Opposite over hypotenuse, right? So we have the square root of 1 minus x squared over 1. Okay, let's write our answer in like a prettier form. So I'm looking at this problem, and it's not, okay, let me just say, there's two different ways that you would have a pretty answer written here. Couldn't we factor out a greatest common factor? If we wanted our answer in factored form. Is factored form or standard form better? Not either or. So let's pretend we wanted our answer in standard form. We would factor out in each term, which, guys, isn't this a term and this a term? So can't I pull out the square root of 2 over 2? So I'm going to pull that out, and then left would be, in my parentheses, what? X minus square root of 1 minus x squared, right? Don't we divide that out if we pulled that out? Does everyone see? That's one way of writing the answer, isn't it? Also, another way of writing the answer was to actually have the square root of 2x over 2 minus the square root of 2. I'm trying to think of how they'd write it. Square root of 2, and then 1 minus x squared, because I multiplied straight across. So I got parentheses all over 2. So then technically we can put this as one denominator, can't we? So then you have the square root of 2x on the outside minus the square root of 2 parentheses 1 minus x squared all over 2. Don't you think it's just easier to write in factored form? I do too. So I would always just write it in factored form if you get to a point and there is a way of doing that.
So is that our answer?
I would write it like this. This is my answer. Now, you guys, obviously we can't find an exact answer, right? If it has variables in it, you're going to have variables in your answer. Does that make sense to everybody? It's like a statement. Like, we're just simplifying. We're not actually calculating. So that's why a lot of times it'll say, write an equivalent algebraic statement, because we're not actually solving. All right, couple more examples. You guys are doing good. We're actually pretty close to being done with the lesson here. So it says, prove that the cosine of pi halves minus x is equal to the sine of x. Now your answer is all in your work. We are told that we should be able to get this side to end up being simplified clear down to this side. So what you would recognize is you'd say, we have a cosine difference problem. So let's go ahead and rewrite this in another form. Now we're just going to leave this alone. That's just where we should end up. So let's rewrite this in an equivalent truth statement. So won't it be cosine of pi halves? Cosine of x? And then cosine has opposite signs, trying to memorize these formulas. And then it will be sine of pi halves, sine of x. That's how we would rewrite it. Now actually calculate what you can. The cosine at pi halves, right here's pi halves. Cosine is x, sine is y. The cosine at pi halves is 0, right? Yes? Yes, true. But so because of the words prove, we have to use math. We're showing where the cofunction identity comes from technically. It wants us to show the math. Good question though, because this is a cofunction identity. That's a good point to make. So we're just showing the math behind y. Alright, so the cosine of pi halves is 0. So we have 0 times cosine of x plus the sine of pi halves is 1. So we have 1 times sine of x. You're showing your work. Isn't 0 times anything 0? So we have 0 plus 1 times anything gives itself. So we have 0 plus sine of x, which is sine of x. And we have now shown the math behind why this cofunction identity exists, basically. All right, so the answer was all in the work. That's like proving an identity, basically. We are proving the cofunction identity there. All right, awesome. All right, so now it says simplify the expression. So guys, because of the word simplify the expression, am I going to be able to get an actual answer? No, there's going to be some variables involved, which that's fine. We've just got to have a most simplified answer here. So you would say this is a cosine difference problem. So tell me how you'd rewrite it. Cosine theta, cosine of 3 pi halves, plus sine of theta, sine of 3 pi halves. Let's calculate what we can. So we have a cosine of theta times by the cosine at 3 pi halves. Right, here's 3 pi halves, cosine is x, sine is y. So we have times 0 plus sine of theta, and then sine at 3 pi halves is -1. So isn't this times 0, 0? So we have 0, and then a positive times a negative is a negative, minus sine of theta. So our final answer is negative sine of theta. Isn't that more simplified than this? Yes, because it's always best to not have something inside your parentheses if possible. Because technically this theta is in parentheses. So you guys see how it's actually really easy? We haven't done any like super advanced math or anything. Okay, let's do another one like that. So tangent of theta plus 3 pi, it says simplify. So we should say, well, this is a true equivalence. It's an addition formula. So this is a tangent addition formula. So let's use this and rewrite it. So that would be tangent of theta plus tangent of 3 pi, and then divided by 1, and then it's a minus, opposite sign, and then now it's times. Tangent theta times tangent of 3 pi. Now remember, where is 3 pi? Well, around the unit circle once is 2 pi. Going another pi in distance, right here is 3 pi, isn't it? Now remember, so right here, tangent of theta can't be simplified. Do you agree? So tangent of theta is tangent of theta. There's nothing more we can do. Plus, what is the tangent at pi? Or 3 pi, same thing. The tangent of pi. Tangent is the y divided by the x. So 0, isn't it? 0 divided by negative 1 is 0. So this calculates to be 0. Divided by 1 minus tangent of theta is tangent of theta, and then we have times the tangent at 3 pi. So won't it be times 0 now? So let's do some math. What would the top become? Tangent of theta. Now on bottom, what will it be? This is 0 right here. 1 minus 0. 1. So our final answer is tangent of theta. So it's really just basic stuff. Okay. This is our last example of the day. The rest of the time will be yours to do homework. When it comes to solutions, you guys, it says find all the solutions. We usually take these steps. Isolate the trig function, make sure, or if it's quadratic, instead we're going to get the trig function equal to 0, correct? Solve by factoring. Now in this problem, notice, you would have to notice, it's going to just be lumped into find the solutions. Now we are going to see problems with addition formulas and difference formulas in them. Now if you're ever asked to solve and you see addition formulas and, difference and addition formulas, you need to rewrite them in their equivalent true statement and then continue to solve. Now guys, people are like wondering, can we put these together? No, these are like this in parentheses and this, like they're completely different, you know what I mean? So there's not a way to put these together. So we've just got to treat them separately. So here's the key with these, you guys. Keeping your work nice and pretty and like paying really close attention to what you're doing. So let's focus in and say, this is an addition formula for sine. Let's just focus on this piece and let's show our work. How would we rewrite just that piece? Sine of x, and then isn't it cosine? Yeah, cosine of pi fourths. And then with sine, it's the same sign, so plus cosine of x, sine of pi fourths, yeah? Now, if it's in your opinion, would you prefer to simplify that now and then move on, or not? Yeah? Okay. So let's rewrite. What do we have here? Sine of x times y, root 2 over 2, and then we have plus cosine of x times root 2 over 2. Okay, good. Now I'm going to move on to the next piece. This one. I'm going to write it underneath. Now you have to remember though, in this problem in particular, it's a plus sign. So I have plus, right? I'm going to do my math under here. So just focusing on brown, how do I rewrite that one? Sine of x, cosine of pi fourths, then it's a minus cosine of x, sine of pi fourths, which we're going to simplify now. So we would say this, we have the sine of x, and then root 2 over 2, because that is what the cosine of pi fourths is. And then we have minus cosine of x, and then times by root 2 over 2, true? And then all that stuff being added together in the end equals negative 1. So let's take the time now to add what we can add together. So isn't this being added to this? So we have sine of x root 2 over 2 plus sine of x root 2 over 2. 2 sine x root 2 over 2, don't we? They're like terms, everyone? There's two of them. So we have a 2 sine of x root 2 over 2's. We've now combined those. Now in this problem, isn't this plus, we have a positive cosine of x root 2 over 2 plus negative cosine of x root 2 over 2. So what happens with those? Yeah, they add up to be 0. Sorry. Yes, they add up to be 0 because look, they're opposites. And then so what does this equal? We were told it was equal to negative 1. Alright. So what do we see happening here? 2 sine of x times by root 2 over 2. Mathematically, what is that? Yes, we're gonna need to isolate the trig function. But guys, 2 divided by 2. Are we guys seeing that? Does it matter the order? No, right? Timesing doesn't matter. So you're saying we can divide these out? So then we have this sine of x root 2 equals negative 1. Yes, now we need to follow what Cynthia said. We need to isolate the trig function. So next step is divide by root 2. So then we're looking for when does sine of x equal negative 1 over root 2. So aren't we looking for when does sine of x equal negative root 2 over 2? We're solving by unit circle, and then remember it did say on an interval from 0 to 2 pi. So let's answer it. So x is equal to, sine is the y value, so the first place that happens is, so 5 pi fourths, and then our next answer is going to be, yep, 7 pi fourths.
And they want radians.
Yes. When we're solving, yeah, we'll always answer in radians. Okay, awesome. Does that make sense? It just took a lot of algebra to be able to get to the place where we could then solve it, if that makes sense. So just pay attention that if you're ever solving and you're given sum or difference formulas, rewrite it and then you'll have it come out nice and pretty. Okay. Awesome, that's the end. So I would go to my paper because the paper is the most updated one with the homework problems. Like, yeah, this is probably pretty close, if not exact, but I would look off my paper because once again, if I've taken off 51, I won't have written it down on here. I will have forgotten to fix it. Just giving an example. So look at your paper and follow that paper. Practicing.